right, let's talk about question 4.20 or 420. Okay, so you see they say that there is a vertical cylindrical tank closed at the bottom and it's partially filled with an incompressible fluid. So I'm going to draw the tank as nicely as I can. I usually draw better than this in real life, in case you're wondering. Okay, and it's partially filled with an incompressible fluid. Remember, incompressible implies that this fluid cannot compress, so everything that enters the control volume or everything that enters must exit a certain volume. So that means that the triple integral term of our continuity equation will disappear. It basically means we're operating at steady state, but we'll get to that just now. It's always just nice to understand what the information tells you. So as soon as you see incompressible, no accumulation, which implies steady state. And that implies that the triple integral is equal to 0. Okay, now let's continue with the statement. A cylindrical rod of diameter di, which is smaller than tank diameter d0. So we've got d0 here and a cylindrical rod here with the diameter di. Okay, is lowered into the liquid at velocity v. Determine the average velocity of the fluid escaping between the rod and the tank walls. So, before we read the next half of the question, let's proceed with this. Quickly, I'm going to select my control volume. So, what I'm going to do is select the control volume so that it's just before the edges of the tank, but also a little bit below the rod. So that way, as the rod moves down, the piece of the little bit of liquid here between the rod and the beginning of my control volume, the liquid here will enter the control volume, okay? And everything that is just before the level of my tank, there will be space for this liquid to actually exit. Let me just draw this a bit bigger. Okay, so that's the shape I'm talking about. And here is the liquid level. And here is the rod. So what's happening is, as the rod moves down, that little gap between the rod and the control volume is pushing liquid in, and the little gap between the control volume and the level has space for fluid to exit. So I have enough space to have fluid entering and exiting the control volume. Now let's put in our vectors. So we know that fluid is leaving, so I'm going to label this as V2, and the normal is always perpendicular to and away from the control volume. So I'm going to label this as N2. Then I know that fluid is entering this way, so I have my velocity 1 like this, and remember that your normal vector is always perpendicular to and away from the control volume. So my normal 1 goes up like that. Now, I'm going to write down the continuity equation. We've already said that the triple integral has disappeared. So the double integral over the control surface of rho n dA, v n dA, is equal to, everything in, is equal to 0. Now, let's begin. I'm going to write down rho. Now, the velocity in is v1. The normal, remember, is 180 degrees away from the velocity entering. So, that means I can write cos of 180 degrees, which later simplifies to minus 1, multiplied by area. Now, the area of liquid that is entering the control volume is the area of the rod. So I'm going to call that A1, plus rho, velocity 2, exiting. Remember, normal, the normal 2 is in the direction of velocity 2. So the angle between them is 0 degrees, so I write cos of 0, and my area is now all the area around the rod. So if I had to draw the tank from the bottom, here's the whole tank, and here's the rod. When I refer to area 2, I'm referring to this area. When I refer to area 1, I'm referring to that area. Okay, so this is area 2, and that's equal to 0. Cos of 180 degrees is minus 1, so I can move it to the other side and it remains positive. So rho v2 cos of 0 is 1, area 2 is equal to rho v1 a1. Okay, And remember, the objective is to find V2, the velocity at which all this liquid is exiting the tank. So if I divide by rho on both sides, that disappears. Let's try solving for V2. V2 is equal to V1 multiplied by A1 divided by A2. Let's keep going with that. V2 is equal to V1 multiplied by area 1 is given by pi over 4 multiplied by the rod diameter squared, di squared. Area 2 is everything around here. That's given by pi over 4 multiplied by the outer diameter, so d outer squared minus d inner squared. And once again, you can see some lovely cancellation happening here with the pi over 4s. Therefore, V2, you can put the bar if you want, it just indicates that it's a vector, is equal to di squared over d naught squared minus di squared. And because for this question they haven't given us any values, this is as far as you can take it. What happens next? This is the velocity relative to the bottom of the tank. Because remember that the bottom of the tank is stationary, so relative to the bottom of the tank, this is what's happening. Now they tell you, we want it relative to the advancing rod. So questions like this I always found very tricky because I never understood what they meant by relative to this thing or relative to that thing. So when they say relative to the bottom of the tank, you know that the bottom of the tank is not moving. So that is quite straightforward to figure out or solve for. The bottom of the tank is not moving, so all velocities are absolute or as they are calculated. But when they say something is relative to something else, essentially the easy way to think about it, which my friend showed me, is pretend that the thing you are moving relative to is stationary. So let's just redraw that picture here. So if this is moving down at velocity v. Oh, and I should also point out here that velocity is entering the tank at velocity v. So instead of labeling this v1, as a final step, you can say v2 is equal to v di squared d naught squared minus di squared. Final answer. Okay, let's continue on this side. So you have something that was initially moving down at velocity v. Because you want the value of the velocity relative to the rod, which has a velocity v, you're going to assume that the rod is constant velocity. Now the only way this rod is at constant velocity is if you add to this velocity v in the upwards direction. That would ultimately cancel out the velocity vector going down. Okay, so if you add a velocity v of magnitude v going upwards, this is now stationary. So that means that every other thing in the system should also receive a value of v, of magnitude v, in the upwards direction. Every other velocity in this control volume should receive a velocity of magnitude v in the upwards direction. So, because in the previous case we calculated v2 is equal to v di squared over d, because we already have this value v2, and that's relative to bottom, then we can say that velocity 2 is the velocity of everything exiting. Remember that? That's how we labeled it on the previous diagram. We said that v2 is everything exiting. All right? So if v2 is represented by this relative to the bottom, then when it's exiting, if everything in the system receives a boost in velocity of magnitude v, then v2 should also receive a boost in magnitude of velocity v. So v2 is actually equal to v di squared over d naught squared minus di squared, and it receives a plus v in the upwards direction. And that's it. If v2 was acting downwards, you would still plus something of magnitude v, provided that up was selected as the positive direction. And this will be relative to the rod. Okay, this was a bit of a long explanation, but I hope it actually makes sense. It took me a bit of time to understand this, But I hope now it makes sense to you, and I hope I was able to help you. If you still can't figure it out, just do what I did and ask your friend for an explanation. You'd be surprised how helpful they can be. So thank you for watching. I hope this helped you.